We'll see how it goes. So I want to talk about pH dependence of enzyme kinetics, and this is something we've thought about a lot. And I'm going to do it over at least 2, maybe 3 classes. And it's all being recorded. So, and I was looking at the previous recordings, and I'm kind of glad that I'm recording it because we forget about stuff. Even I forget what I put on there. So it's nice to go back and look at that. So if you go to the first textbook, and I'm sure in any detailed enzyme kinetics, there's always at least one chapter devoted to the pH dependence of enzyme kinetics. And it's something that our lab has thought a lot about over the years. And so the reason it's an important topic is that pH can affect enzymes in a number of different ways. And I think the one I'm going to talk about today is they can affect the functional form of a general acid and a general base. And so we already talked about what those are. Remember, general acid, it's the traditional Bronsted definition of an acid. It's a proton donor. And so in order for a general acid to donate a proton, it has to have a proton to donate. Okay, it sounds obvious, but that's where a lot of the pH dependence comes from. And a lot of times the pKa's are near neutrality. That's the most optimum value. And likewise, the functional form of a general base is, since it's a proton acceptor, is the deprotonated form. And so a lot of the pH dependence arises from that. And since I'm talking about it, I can just, in words, give the argument as to why a pKa near neutrality, or in general, if you're not even working on biological enzymes, just catalysts, near the pH of your reaction is optimal. And that is, on the one hand, you could think, well, an acid would be better the more acidic it is. So in terms of the amino acids, you might think a good general acid might be aspartate. It has pKa like 3, something like that, carboxylic acid 3 or 4. It's pretty acidic. It's willing to give up its proton. But at neutral pH, there's very little of it in its functional form. It's already deprotonated, so it can't donate a proton. So then you can go to the other end of the spectrum and go up to lysine or arginine. Say take arginine, pK is what, like 12 or something? 12. It's going to be fully in the functional form. It's going to have a proton, but it's not going to let it go. And so the compromise is to have the pK near neutrality. It's mostly in the functional form, and it's willing to let it go. So histidine, or one of the other amino acids that has a pK that's perturbed by the local environment, to have a pK near neutrality. And they'll often happen away from neutrality, but with a penalty. Same argument holds for nucleotides, and it would hold for a non-biological polymer as well. So that's where I'll talk about the pH dependence of enzyme kinetics. But there's another source which is important to be, and there may be others. These are the 2 that come to mind to be cognizant of, and that is the effect of pH cannot connect to desktop. Resume recording. There we go. Okay. Right. And so this is the effect on folding. And so once you go to extreme pHs, you begin to denature any biopolymer that depends on hydrogen bonding for stability. And I always like to think about it as if you have a hydrogen bond like this, and that hydrogen bond is holding the enzyme together. If I take and I go to basic conditions, high pH, then what's going to happen is I'm going to deprotonate the donor. And I can't have the hydrogen bond. so the molecule might unfold or something. And if I go to low pH, I'm going to protonate the B. And then I also cannot have a hydrogen bond. And I'm also going to denature. So it's pretty common that all proteins can be denatured at high pH alkaline denaturation and at low pH acid denaturation. And this is a real simple way to think about it. But often there's multiple hydrogen bonds, and those pKa's can be perturbed. And so the mathematical form for the coupling between biopolymer folding and pH is more complicated and has to go to binding polynomials, and I know we talk about it a little bit in your class. And actually wrote written papers on both of these. On topic one was the paper that published in 2003 in biochemistry, and I wrote that by myself actually for Christmas break one year. Must have been Christmas of 2002. The year I was up for tenure and needed a paper, so it turned out to be really influential, interestingly enough. And then number two, actually wrote that paper with Juliette Lecomte when she was here, and so and with Ellen Moody. And that first one's published in biochemistry, and the second one's published in RNA. Kind of interesting. Okay, so let's go into a new page. And so I said we're going to start out just looking and thinking about the effect of pH on single residues. And just going to start out with one residue. Okay, so we'll, since everyone here writes RNA, we'll use R for enzyme today. So R for ribozyme, for enzyme. And let's say it can exist in two different forms, protonated and deprotonated, like that. And let's say that H represents protonation of a general base, and so the left-hand form is non-functional and does not react, but the right-hand form is functional. That general base can now accept a proton, and so we'll let this guy go on to form product. And that's all there is to it. And I always kind of think back to Ken Dill in the Statistical Thermodynamics book, and he says, most problems, no matter how complex the mathematics, are rooted in a really simple model. And this is very simple. It's a three-state system. Protonated general base cannot give product. Deprotonated can give product. In reality, it's probably more complicated than that. The protonated one might also give product, but it might do it more slowly. So we'll start with this, what I'll call a one-channel mechanism, where let's see, I'm supposed to be able to. There we go. I've got a pointer. A big pointer. That's the channel right there. Okay. So that's a one-channel mechanism. And so we'll go ahead and write down the, let's shrink that down. And write down the equations for that. Okay. So we all know how to do this. The velocity is equal to dp dt. And we need some rate constants in here. And so, maybe we'll call, Eric, I'll call this the rate of chemistry, although as we know, there could be multiple steps in there. I'll just call it Kchem, or Kc for Kchem. And then this equilibrium at the top is just an acid dissociation constant, so it's going to have some sort of pKa with it, but I'll write it down as Ka, and we'll come back to that. So we know dp dt, since it's only connected by a single arrow from R, is just going to be equal to Kc times the concentration of R. And so I went back in the notes to remind myself how we had, I think it was lecture 2 from the summer, we went through a partition function approach to enzyme kinetics and went back and looked at that. And basically we went, the math I used, and I'll just put it up here as a reminder, is we went down to the fraction of R, and that's equal to R over R total. And there's only 2 species, R and RH, so we can write it like that. Over R naught. And then solve for R and substitute it into the above equation to give that the velocity is equal to Kc times Fr times R naught. Okay. And this rate is equal to the rate of formation of the product here. But it's also equal to the loss of the reactant, so I can write down over here minus dr dt. I can write it here. I'm going to choose to write it here. Okay. So on the gel, we just see loss of the total ribosome. And so when you look at this, you can see immediately that this is first order kinetics. It's not even pseudo first order, it's true first order. And that the observed rate constant is going to be this constant here, which is F sub R is constant for a given pH, but it's parametric in pH. So that's K obs. So we can rewrite this as, we can write that as K obs. And you guys will recall that if we take this and we solve it, we would get an equation that would be F sub R is equal to E to the minus K obs T, where K obs is Kc times Fr, and we would just plot it like this. And we get out a T1 half. From this we can get out K obs just by fitting it. Alright. Oops. Fix that. Alright. So what we're interested in is K obs. So K obs is equal to Kc times F sub R. And let's see, how do I want to, maybe I'll work down. And so we'd like to get that in terms of the pKa and the pH. So we should write down the Ka. I could have done that right away, but I'll go back and do it now. I have a little spot right there. Maybe I'll put it right here. And we all know what a Ka is, because it's an acid dissociation constant. It has concentrations of molarity, so it's R times H over RH. Like that. And so when you look at that, one thing when I look at those equations now, right now, I see a ratio of R to RH. And so I'm going to actually write that. I'm going to squeeze this down a little bit. And go ahead and solve for this. And I'm just going to rearrange it. I already worked through this earlier, so I know what I want. I'm going to rearrange it and solve for RH over R. And that's equal to H over Ka, right? So I can even box this. So I've kind of got that on the side. I can grab that. And so I can rearrange this guy down here. I can rearrange that in terms of RH over R by dividing through numerator and denominator by R. So I'll go ahead and do that. And end up with that. Okay, 1 over R times 1 over R, same as multiplying by the number 1. So now I can substitute in. Like that. And in a sense I'm done, but it's nice to have pH and not just H. So so there's a trick that I like to use, and just write down the definition of pH. And then solve that for H. Okay, so it's H is equal to 10 to the minus pH. And likewise, Ka is equal to 10 to the minus pKa. So therefore, H over Ka, if we look up here, this is what I need to write. H over Ka is right there. So I can get H over Ka down here is 10 to the minus pH divided by 10 to the minus pKa. And if they have a common base, when you divide, then you can subtract the exponents. And so, so that's just equal to 10 to the minus pH minus pKa, but what's typically written this way. 10 to the pK minus pH. So in some ways, we can box this guy. And then we're going to take this and we're going to substitute that in for that term right there. So that's what K-obs is equal to. Kc divided by 1 plus 10 to the pK minus pH. So go ahead and plot it. I'll do that on, let me grab this equation and I'm going to copy it over onto the next page. When we plot these, we almost always plot log of K-obs because it's linear in free energy. So remember, free energy is delta G equals minus RT, the natural log of K, or it could be 2.303 log of K. So we like to take the log. And if we're going to take the log of one side, we have to take the log of the other side. And so when you go in and you fit your data in a nonlinear program like we use Kaleidograph, you actually have to take the log of this whole beast right here in the input. And that really can't be simplified any further, so I just write it in like that when I'm programming it. And so now we can plot that. Log K-ops versus pH. So you do an experiment at pH 7 and you get a data point. And you do the experiment at pH 6 and you get another data point, and so on. And it should look something like this. And when you fit it, okay, that equation can do that trick right there. And so we can just think it through as to whether or not it's behaving itself properly. And so in the example that I've given right here, the pKa is near the rounding point of the curve. And so I just picked one where the pKa is about 7. So when the pH is much greater than the pKa, so we can go up here and look at the equation. So if the pKa is 7, so let's say the pH is 9, then we get 10 to the minus 2, okay, which is 1 plus 0.01, which is 1. That means it's leveled off. And it's leveled off at log Kc. So we know that this asymptote here is the log of Kc. So we can pull out the intrinsic rate of chemistry from that extrapolation according to this model. And we can check out the other extreme. When the pH is less than the pKa, so assuming the pKa is 7, let's say the pH is 5, then we have 10 to the 2. So now we have Kc over 101 or over 100, and so it's down by 2 logs. And if the pH is 4, it'll be down by 3 logs, so it's dropping log linearly. And moreover, the slope of this line is an important point. So we can go back for 1 second, and this is something Erica's thinking about right now, and do a hill treatment, and then we'll talk about the fact that these are always fuzzy, but everybody does them. Okay? And so we'll just go back to our model. And I actually didn't write the proton in here, but I'll go ahead and do that. And let's say that, it's plus H plus. But let's say that maybe we don't know that there's 1. Maybe there could be 2. So we'll leave that as a variable, n, like that. And then that means there's n of them bound here. But there's really a set of n equilibrium constants, Ka1, Ka2, if there's 2 of them, that I'm not showing. And it's almost impossible to tell them apart from each other. And so usually people leave it as Ka, and then when you go down and you write the equilibrium here, there's an n that ends up in the exponent on h by the law of mass action, right? So in other words, this n and that n are the same. And some people will also raise this k, and I typically do, also to the nth power. Yeah, sorry, I'll get my pointer here. This n, because there's n of those multiplied together. But the nice thing that happens is when you solve for r over rh, those are not to the nth power, and these are both to the nth power. And so in the math, what happens is it doesn't change much, other than these are collectively raised to the nth power. Each one is to the nth power, so you can pull it out like so. So if we go in and we look at our math, it doesn't. It disconnected again. It still says it's still recording. Okay. It doesn't show up until this point right here, and then these guys are both to the nth power. Okay, I'm right there. And then, okay, so if h is to the nth power, we can go down to our little math here. Sorry, yes. Then it ends up being minus n log of h. Which is n times the pH, like that, on both sides. So you end up with an n here. And an n there. And so when I go up to the next page, I'll keep that n. So then in this plot, let's go back and think this through in terms of the limits. So when we're in the limit of the pH being much lower than the pKa, then we can ignore this term because it's like 1 plus 100. And so it's actually the log of A over B, which is the log of A minus the log of B. You can show that the slope in the pH plot is really n. So this slope here, I don't think I'm going to go through it, but that slope is n. So there's actually three things that you can get, that you can solve for when you're doing this in kaleidograph. You can get out the intrinsic rate of chemistry, right here, as log Kc. You can get out the pKa, and you can also get out the Hill constant. And if life is good, the Hill constant is 1. And sometimes it is 1. And when we've done these and the Hill constant's 1, then we don't actually put in n. We don't have an n. We just let it be 1 and the fit is good. And sometimes we note that the fit is good and that it's log linear. And if it's 2, then it's pretty easy to interpret. The problem is when it comes back as 0.5 or 0.6, which it does sometimes. It's hard to come up with mechanisms to handle that. And that's what Eric is facing right now in one of the cases. People usually come back, they throw up their hands, and they say that it's due to kinetic complexity. So I'll give you a scenario right now, a slightly more complex scenario, if everybody's good with this, where we can think about how to handle this. It's worth noting, if I just go back here for one second, that if we were to take this model right here and instead put the reactive channel off the protonated form, then the equations would be very similar, okay? Except that the line, instead of sloping up and leveling off, would be level and then slope down, all right? And so maybe it's worth doing one last thing, and that is looking at this form and seeing if this makes sense. So if this is a general base, let's say this is a histidine and it needs to be deprotonated, then it makes total sense. Because when the pH is 6, only 10% of it is in the deprotonated form. And when the pH is 5, only 1% is in the deprotonated form, and so on. When the pH is 7, 50% is in the deprotonated form. When the pH is 8, I think 99% It's 1 unit above the pKa. 90%, sorry, 90% is in the, so 10% is in the non-functional form, then 1%, then 0.1%, and so on until it's level. One of the things that it's kind of notable about this is if everything's working really well, you can do things with enzyme kinetics that you can't do by spectroscopy. And that is that you can look at the population of the functional form when it's really rare. So when it's 1% or 0.1%, if it's still log linear, it's hard to do that by NMR. It's hard to do that by another method, by fluorescence. When we were doing Raman crystallography, you could never do that because there's problems with detection and signal-to-noise issues and so on. But here, because you just wait long enough and it reacts, and so it's interesting in that respect. So if everybody's good, I'll throw one twist in it, and then I think that'll be it. Okay, so all right. So here's the twist. Let's go to a new page. So we'll go back. Actually, I'm going to go all the way now. Yeah. I made a bit of a mess here, but I think I can grab this. Yes. Okay. So right now I just pasted in the same mechanism. Missing part of my P. Like that. Okay. But let's say that the protonated form can also react, especially in ribozymes. Enzymes are more promiscuous often, especially ribozymes, than I think is commonly appreciated. And so this guy might also go form product. Let's think of an example. So let's say the general base is a deprotonated guanine. And the guanine, when it's protonated, we say the reaction's 0. But maybe buffer can come in and deprotonate it, albeit poorly, or water can come in and do it, or there's dynamics and another base goes in some of the time and does the reaction. Okay, so that also, and it goes and forms the same product. We'll call that a second channel. And I'm going to go ahead and use descriptive names here on the rate constant. So I'll call this Kf for K fast, and this Ks for K slow. And so we can ask ourselves, what equation would we use to describe this, and what would the plot look like? All right. So remember, we just did that K obs was equal to K. We had Kc, but now Kf times the fraction R. So when only R reacted, that was the equation we used. But it turns out it's just the sum for channel reactions. It's the sum of the different channels. So there's an equivalent term for the left-hand channel, and that's Ks times the fraction of RH. And so with the partition function approach, it's really trivial to write down the expression for this. And so it's really just a question. Let's go over and deal with the second term first, because that's the one we already handled. We know on the previous page, I'm sorry, it's the first term that we handled on the previous page. It was Kf times 1 over 1 plus 10 to the pK minus pH. In fact, we don't need that 1 there, right? Because it's a 1. So, so the beauty of this partition function approach is that the fraction of any species is that term over the partition function. So here, that's why we can think of this as this 1 and this 1 being the same 1, all right? And so then the weight over here is for, that's the same denominator, but it's this term that needs to go up here. So that's the rate equation for this model. It's interesting, I pulled up, oops, not sure what just happened. Uh-oh, something bad just happened on my, I'm having problems. It's been connecting and disconnecting, and I'm going to pause this. This is going to be a bit of a patchy recording, so I'm not sure what happened, but back on this page here, let's see if it'll let me fix it. Okay, 10 to the pk minus ph, and then this guy has the same partition function, so it has the same denominator, and then this term goes up into the numerator. So I was going back and looking at something we wrote for a chapter for Ken Johnson years ago on doing ribosome kinetics, and it had something in here, but I didn't have quite this, what I would say, sort of formal way. I wasn't thinking about things as clearly then as I can think about them now, at least in my mind. And so I had done a different way. Got the same answer, but I don't think it was as easy to understand as this is. But what I put in there is I took this second term here, okay, and simplified it down. And so you can multiply the numerator and the denominator by 10 to the ph minus pk. And you can end up with that expression, right? So when you do that, in other words, this term goes to 1, this term goes to 1, and then this term becomes this term. So when you plot this data, it's kind of interesting. Again, you plot log k obs. So I haven't taken the log, but if I did take the log and I did do this in Kaleidograph, I would take the log here. So I'd have to take the log of this whole expression and write that in. There's no way to simplify that down. And what happens is, I'll just write the answer. It ends up looking like that. Alright, I didn't write that. Let me try that one more time. Or at least erase. This should be smoother in here. Like that. Now, the pKa on this is here. And if that pK is 7, then we can sort of understand it in the same way that we understood the last one, except now something new happens at really low pH. So let's say the pH is dropped to 5. Then what's happening is that this guy is now Kf over 100, and this guy is now, he's gone to, this term has disappeared, right? So it's now 10 to the 5 minus 7.01. So this term has become Ks. It's constant. And this one's dropping and dropping and dropping. And at some point, it will drop below that value. And so, in other words, what's going on behind the scenes is the fast channel, the left channel, is doing this. And it's going on forever. Dropping, dropping, dropping. And when it drops below, you can show asymptotically that this guy here is the log of K slow. And this one is the log of Kf. It'll eventually level off. And an important point is that this rounding point here is not a pKa. And there's some cases in the literature where people have thought that those are pKa's, but they're not. They're a change in the productive, in the major reaction channel of the reaction. And even worse, some people in the literature have taken this picture and tried to do, and Scott, I think you probably know, maybe even from your class, you know, if you're doing a standard pKa, like an NMR titration or Raman titration or CD titration, and you have some signal versus pH, right? And it goes like that. We've all seen plots, sigmoidal plots like that. And we all know that the midpoint is the pKa, right? And there's a single pKa. And that's fine if that signal comes from a spectroscopic experiment. But in the model here, and this is a really important point, this midpoint here has no meaning at all. Okay? And so down here, we know that if the Hill coefficient's 1, then we kind of, if we go 1 pH unit above the pK, we're 90% in one state, we're 90% in the other, so we like to go 2 units to the right to get the 99%, 2 units to the left to get the 1%, and the pK is in the middle. Here, it's the rounding point that could be the pKa. Here, in this case, this rounding point is not a pKa, and then this midpoint, where that midpoint shows up, it doesn't have to go over, these rounding points don't have to go over 2 logs, they could go over 6 logs if the rate constant for the slow channel is really slow. You have to drop the pH a lot before it actually will kick in. So, so we've gotten embroiled a little bit in some debates on the literature on this, and when we originally did the pH-coupled RNA folding and unfolding, I was doing that with Juliet. We also made those points, tried to make those points really clear graphically where those pKs come from. I'm going to stop there. Plus my gizmo's been giving me problems. I'm not sure how the recording went. I hope it went okay. You guys have any questions? Oh yeah, I didn't bother with n here, did I? But it would be the quantity pK minus pH would be multiplied by n in every one of those terms if you needed to. If it's not multiplied by n, it really is. It's just multiplied by n equals 1. You can think about it that way. I mean, the other way you can simplify the math that I would prefer to do, I prefer this form. I'm still recording. I prefer this form, And it has a common denominator, right? So you could actually add these two guys together and just put one of these in the denominator. And then you can clearly see that there's an AB form here, and that one of the terms is multiplied by KF and the other term is multiplied by KS. And that's a nice way to think about it. And as you read papers, if you see a three-state type of model in spectroscopy or something like that, you'll have three terms in the partition function. You also have three terms in the numerator, but each of those three terms, which are the same ones as are in the denominator, are multiplied by a coefficient that represents some sort of a factor, scaling factor for that particular channel. So, I can try to say, oh yeah, there's some messed up stuff that went onto the other pages, but one of the other things that we've tried to do is not only take this approach for pH dependence, but also for magnesium too. So you can easily write down models. You can see how simple it is to think about it and write the models down. And you can write down a 3-channel model, say for magnesium. No magnesium's bound, 1 magnesium bound, 2 magnesium bound, and then as the data requires, you can have multiple channels. So, okay, stop it. That has 2 binding sites, and I started with them already bound, so I'll just, maybe I'll put one at the top and one at the bottom. Okay, something like that. So that's how you would do it. And there's the microscopic, macroscopic binding constants and all that you can get into. Like that. And there's lots of things. All those pKs can be different from one another. There could be 4 different pKs related by a thermodynamic box. But the model, just for simplicity, assumes that all those pKs are the same. Oops, my bad. Yeah, my bad. And so, if you write out what RHH, put one like this. That's equal to the Ka, and that that's also equal to the Ka.
So
Then
just cancel with the
you can multiply these two equations together, and what will happen is you'll end up with R times H squared over RHH equals Ka squared, because it's Ka times Ka. So that's where the square comes from. I'm simplifying. I'm oversimplifying things because there's microscopic. Remember the microscopic constants and the macroscopic constants, and so, for example, it depends on whether or not you can distinguish between this guy and this guy. So you might be doing an experiment where you can, you might be doing one where you cannot. Okay, like in a ribozyme reaction, you probably cannot. Maybe in NMR, if you're lucky, you could. But if you can't, then really here you don't write RH, you write the sum of R superscript H plus R subscript H. And you put a 2 in there, and then one of these ends up being divided by 2, one ends up being multiplied by 2, you remember that? But then when you multiply them together, the 2's cancel, so it doesn't matter anyhow. So I'm kind of skipping that. But that's where it comes from.
You can find it derived from a couple points of view, and you think that's where it is.
Yeah.
It's exactly the same thing.
Yeah. So that's where it comes from. most of, so so with all that said, I can tell you how things go down in the literature. They don't always go down the way they do on you know on class lecture or text like they do here. So some people don't plot log of k-obs. They just plot k-obs, and there's a, it's kind of okay. Okay, so if you say, write down the equation again. Well, just a simple one for the one channel. What was it? Log k-obs equals, log. Let's get rid of all logs. Let me start over. Just k-obs equals kc over 1 plus 10 to the pk minus ph. So now, for me, these days, when I look at an equation like that, I immediately know it's a two-state equation because there's two terms in the denominator, okay? And so I said you should take the log of both sides. But some people don't do that. And so, so we already know what the log form looks like. But if I don't take the log, what does it look like? It's still going to be asymptotic at high pH.
But it'll go up much faster.
Yeah, it'll look like this. And that's because this portion over here, where the rate's super small, you can't tell the difference in those values here because they're all jammed into this really tiny area. So it'll end up looking like this. And then the pKa will be at the midpoint. Because when the pH is equal to the pKa, you get 10 to the 0, which is 1. So you get k-obs over 1 plus 1, or kc over 1 plus 1, or kc over 2. So it actually, in this instance, if you plot the data this way, this is equal to the pKa. And so some of our colleagues, like David Lilly as an example, never takes the log. And if you take his data and you take the log of his data, it doesn't look like this beautiful classical form over here. It looks more like the one that I had up a little while ago, where the log k-obs versus pH also looks sigmoidal. But it should never look sigmoidal according to a two-channel mechanism where only one channel reacts. But it will look sigmoidal, but not truly be sigmoidal, because it's not that behavior if it's a two-channel and there's a leaky first channel. And I think a lot of times that's what's going on, and they don't want to deal with it, so they just plot it as k-obs, and when they do that, it buries all the bad stuff down under here so you can't see it.